Hi students, this is lecture 7. Now it's about network simulation packages. In this lecture we are going to visit some important network simulators that is available on the software shelf, as they say. As noted earlier, block 5, 4 to 7 are very important, dependent on the choice simulation. This is related to the lecture number 3 or 4. Some examples of academic simulators include the following. We have the first simulator is REAL. It's a simulator for studying the dynamics behavior of flow and congestion control schemes in a packet. Switch data networks, network topology, protocols, data, and control parameters are represented by scenarios which are described using net languages as simple ASCII representation of the network. About 30 modules are provided which are exactly emulate the actions of several well-known flow control protocols. Net language is one of the common languages that used by many simulators. It's like simple programming language used for networking language. The second simulator is called Insane. It's a network simulator designed to test various IP over ATM algorithms, which ATM here is like asynchronous transfer mode networks. We don't usually see this in the labs or everywhere. It's sometimes used between towers or between two big communication servers, etc. With realistic traffic laws derived from empirical traffic measurements. Its ATM protocol stack provides real-time guarantees to ATM virtual circuits by using rate control static priority RCSP queuing, a protocol similar to real-time channel administration protocol RCCAP or RCAP is implemented for ATM signals. A graphical simulation monitor can provide an easy way to check the progress of multiple simulation processes. So in short, Insane deals with ATM protocol or ATM based machines. Some examples of academic simulators include the following. NetSim, network simulation. This is not free. It's available by many universities actually. It is intended to offer a very detailed simulation of Ethernet, including a realistic model of signal propagation, the effect of relative positions of stations on events in the network, the collision detection and the handling process, and the transmission deferral mechanism. However, it cannot be extended to address modern networks. It has some limitation. Okay. The fourth network simulator is MAIS, which is a C-based language for hierarchical simulation, or more specifically a language for parallel discrete event system. A logical process is used to model one or more physical processes. The event in the physical system are modeled by message exchange among the corresponding logic processes in the model. Users can also migrate into recent extensions like Parsec or Manmus, an object-oriented extension for MAIS. Okay. OpNet is an optimized network engineering tool. It's one of the most important and useful simulator. Is also paid, and it used to have a free version for called ITGoro, but they canceled it now. It's an object-oriented simulation environment that meets all these requirements and is the most powerful general-purpose network simulator available today. Simulation Java or SimJava is a discrete event process-oriented simulation package. It's an API that augments means that it adds Java with building blocks for defining and running simulations. Network Simulation 2 is old version of Network Simulation 3, is an object-oriented discrete event simulator targeted research developed by University of California, Berkeley, and written in C++ and OTCL. These are somehow old programming languages and they are difficult to learn now by most researchers. Instead, we are using the version 3 now. They called NS3. Okay. Simulink is a platform for multi-domain simulation and model based on design of dynamic systems. It provides an interactive graphical environment, a customizable set of block libraries that let one accurately design, simulate, implement, and test control signal processing communications. Other time variant system. It can also be extended for specifically specialized applications. Simulink is an extension for MATLAB, which uses an icon-driven interface for most researchers use Simulink in many other applications, not just like networking, but supports networking as well. Some modules of Simulink inside MATLAB can be easily used for network purposes. Now we have to visit more thoroughly OpNet network simulation package exercise. Okay. The purpose of this exercise is to understand how a framework operates under the hood. Before we embark on this task, it will be illuminating. Embark means start. Means it will illuminating to consider the feature offered by the professional grade event based network simulation tool as a gold standard of comparison. The simulation tool we have in mind is OpNet. Okay. OpNet, which stands for Optimized Network Engineering Tools, has achieved widespread use in academia, industry, and government. The U.S. Army adopted OpNet as a standard under the auspices of the remainings of Army Enterprise Strategy under the leadership of U.S. Army Office of Director of Information System for Command, Control, Communication, and Computers. OpNet was one of the most expensive network simulators available today in the market. OpNet is widely used in universities as well as many parts of the Department of Defense, DoD. OpNet supports visualization through model-directed objects. It may be described as a communication-oriented simulation language. The single most important significant aspect of OpNet is that it provides direct access to the source code coupled with an easy-to-use front-end. Okay. OpNet, a network simulation package exercise. A generic approach to network modeling can be constructed using the OSI reference model. You all know Open System Interconnection, OSI reference model, as its basis, as shown in the figure 5.6. If you remember the 7 layers of networking, the application, presentation, session, transport, network, data link, and physical. This approach allows the implementation of different network protocols which are compatible with an OSI layer boundaries. Pedagogically, which means that in teaching or in the relation between a teacher and the student, this approach has limitations. As illustrated in the 5.6, any detailed implementation of the Ethernet model will not directly align with the OSI reference model. Other protocols such as fiber or distributed data interface, FDDI, also do not perfectly align with the OSI reference model. It means that there are some small limitations that we can encounter using OpNet because these things are not transparent. You can't see it real in the encoding. For example, this Ethernet LCC layer and FDDI protocol architecture. The OpNet simulator is more related to the network and transport of the application layer, more than to the physical layer. OpNet models are composed of 3 primary model layers: the process layer, the node layer, and the network layer. The lowest modeling layer is the process layer. Process layer, STD that defines a node, node models, individual nodes on stations, network models, networks on subnets. These are the main 3 layers of OpNet. Okay. The first process model, which is shown in figure 5.8, shows a state transition diagram STD for the generation of packets. Process models are built using finite state machines. If you remember finite state machines from logic, FSMs, described by STDs. FSMs are effective means of defining discrete event systems. We all know as FSM, finite state machines are dependent on events other than time that maintain state information. FSM-based design provides a means to manage complexity. Complex systems can be broken down into individual states, and then each state is defined and implemented. Okay, we are still in the process layer. The next level of abstraction from the process model, you see the icons here. If you press any of these icons in the OpNet model, you will go to this basic diagram, which is the finite state machines. These finite state machines are encapsulating using these blocks, which are somehow not understandable as well, but you can figure out what these are responsible about. Okay. Each element in the node model either are predefined OpNet artifact or defined by its own STD. Sometimes if you press double click for the node model, you will not get finite state machine because it might be the simplest way of representation. Okay. Figure 5.9 is an example of a node model that defines a station on an FTDI network. A physical transmitter, physical receiver, the MAC layer, and we have two sink and source of packets. That means a packet generation and packet receiving nodes. Packets are generated from the source LLC, processed in the MAC module, and are put in the ring by physical TX module. Traffic from the ring is received via RX module and processed inside the MAC module, and then finally received by and discarded by LCC sink. Okay, the heart of the node model is either process module or a queue module. Processor modules, they are different. Processor modules are used to perform general processing of data packets as specified in the typical protocol, while queuing models are supersets of processor module with additional data collection capabilities. The MAC module in the figure is an instantiation of queue model. This MAC model is an instantiation or definition of the queue model we are talking about. Okay. Now let's jump to the last network model, or the highest modeling layer in this OpNet. These are sets of icons or figures that are understandable by the students. For example, this is a PC. The network model represents the hierarchy of subnetworks. A network model is shown in figure 5, which each station node is defined by a node model, such as. In short, if you press double click for this model, you may see this set node model. Each node model can be represented by FSM state machine, which is STD.